Okay, so now we're gonna kind of come back to more of our mathematical description of phases and get a little bit more detailed in understanding the role of pressure on the temperature of phase transitions. Okay? So recall at the beginning of this module, we talked about how a graph of chemical potential versus temperature, and the slope of that is the negative entropy, right? So partial of mu by partial of T at constant P is negative molar entropy, which is what each of those lines describe. And where the chemical potentials are equal, that's where a phase transition occurs. And the phase with the lowest chemical potential at a given temperature is the one that is observed. So what we want to try to do is come up with a predictor or some kind of qualitative way of figuring out what's going to happen to this melting point as pressure increases. So to do that, we rely on the following equation that we derived a few videos ago, which says chemical potential at the final pressure equals chemical potential at the initial pressure plus RT natural log, let me write that a little bit better, natural log of PF over PI. And in the case where PF is greater than PI, right, as can be seen, the natural log of a number greater than 1 will be positive. So overall, if PF is greater than PI, then the chemical potential will increase. So then mu at PF becomes greater than mu at PI, with PF being greater than PI. So now what does that do to this graph? Well, because it's we'll treat it as this constant slope. If I look at the solid phase, all of my chemical potentials will have been increased, right? So it might look something like this, okay? So now similarly, if I look at the liquid phase, all of my chemical potentials will also have been increased, okay? Something like that, some more or less constant increase. And now hopefully what you can see is where the new chemical potentials have intersected, they have gone out to a higher temperature. Thus, for most materials, as P increases, so does the melting temperature, okay? And now, as we might imagine, if we look at the other phases, right, and this whole idea, if chemical potential has increased all the way around, right, we'll draw those increases for all of those phases. You can see now, if I look at all those new intersections, right, this intersection has now shifted to higher temperature. Lovely, okay? And now this intersection has also increased to higher temperatures. So also the boiling point has increased with increasing pressure. And in a lot of ways, when you think about it, that makes good sense, because when we're increasing the pressure over material, we're compacting it, and it's making it more difficult to rearrange itself into a new phase. Therefore, it requires more heat. It requires a higher energy to do that. So it needs to happen at a higher temperature. So again, this is what our normal situation looks like that we just described, where chemical potentials for the solid and chemical potentials for the liquid increase. And in this normal case, the molar volume of my solid is less than the molar volume of my liquid, or another way to say this is solid phase is more dense, okay? Is more dense. So this is the case with most materials. However, our exception to that is water, okay? So with water, the solid phase, the molar volume of the solid is actually greater than the molar volume of the liquid, or in other words, the liquid phase is more dense, okay? And so now you notice what happens here. Overall, the chemical potentials of the phases have still increased with increasing pressure, right? There's my low pressure on the solid, and there's my high pressure. However, what we should notice here is in this case, this exception of a case, the chemical potential of the solid increases massively with increasing pressure. And the chemical potential of the liquid does not increase nearly as much as it did with that regular case. So resultingly, what you can see is when we look at where the low pressure samples intersect down here at the red versus where they intersect at the blue, they are intersecting at a colder temperature. Whereas in this normal case, right, the low pressure intersected down here and the high pressure intersected there at a higher temperature. Right? So that's fundamentally interesting for water, and it has everything to do with the hydrogen bonding network and this interesting observation that the liquid phase is more dense than the solid phase. Okay, more on phase boundaries and phase transitions in the coming videos.